dear students, welcome to physics class. Okay, so yesterday we had discussed the Young's single slit experiment. So that single slit experiment to demonstrate the phenomena of diffractions. Okay, double slit experiments for interference. Okay, now we are going to see the validity of the ray optics. So for what are the cases the ray optics is applicable, for what are the cases the wave optics is applicable, in which situations we used to specify the word ray, under which situations we used to specify the word ray, that only we are going to see. From the simple example, let us take an aperture or a slit. Aperture is nothing but a slit or a small hole. This is a slit or an aperture. So an aperture is nothing but a slit or hole which was illuminated by monochromatic source. So from the monochromatic source, the parallel rays are incident. After incident, then the secondary waves are originated from the slit. Then the diffraction phenomena is observed on a screen which is located far away from it. So let G and G dash is the screen, a point P in which we have to observe the diffraction phenomena. Okay, right? Okay. But in the case la நம்ம எடுத்துட்டு இந்த slit ஓட thickness பாத்தீங்கன்னா it's a A is a slit width. So in this case the slit width A is illuminated by a source, then with a parallel beam, then the angle of diffracted beam, then the angle of diffracted beam. What will be the angle of diffracted beam? That already we have found, that is theta, which is equal to lambda by A. So what is the theta here? So in the previous class we had discussed where theta is, it is an angular size. Theta is an angular size of bright central maximum. நமக்கு சென்ட்ரல் வரது எப்படி இருக்கும்? It's very bright and central maximum. Bright central maximum. Okay. Suppose in traveling a distance is that the diffracted beam occurs the width. அப்ப இந்த width-ஓட அது travel பண்றது. If traveling a distance is that the diffracted beam, the diffracted beam occurs with what is the width? Z into lambda by A. So that is the width. That is the width. What is the width? The width A is equal to Z lambda by A. Also, so this gives the distance beyond which the divergence of the beam width. Okay. So basically, what is the minimum distance? Okay. So this is a minimum distance of diffractions where Z is minimum distance of diffractions. So we can get the Z. So Z is equal to A into A square lambda. Sorry, A square by lambda. So here Z is it was given by the scientist Fresnel. So it is a Fresnel distance. So we can say it is ZF. So it is a Fresnel distance, which is nothing but the minimum distance of diffractions. Minimum distance of diffractions. So அப்ப நம்ம இதுல என்ன கால்குலேட் பண்ணிருக்கோம்னா diffraction phenomena யூஸ் பண்ணிட்டு இந்த diffracted beam அது கிரியேட் பண்ற angle according to the particular width of the slit, what is an angle made by it. So அப்ப உள்ள விழுகிற இன்சிடென்ட் லைட்டுக்குன்னு ஒரு வேவ் லென்த் இருக்கும், then slit ஓட width இதில இருந்து நமக்கு theta calculate பண்ணிருக்கோம். So the angle of the diffracted beam, that is theta is equal to lambda by A, where lambda is the wavelength of the incident parallel beam. This is incident parallel beam. This is incident parallel beam. This is monochromatic source. S is the monochromatic source. So from the monochromatic source, the parallel beam of wavelength lambda, which was used to illuminate the aperture is nothing but a slit or hole, having the width A, அதோட width வந்து A, and then the diffracted is obtained on a screen G dash at a point P. We should determine the diffractions. Inga, what is the theta? It is the angular size of the central maxima, which is a bright. Okay, so if traveling a distance Z, the diffracted beam occurs the width upon the width oda sethi thana. So what is the width? It is Z lambda A. So அந்த widthங்கிறது எதுக்கு ஈக்குவல் Z lambda A. இதில் Z அப்படிங்கிறது Fresnel distance because it is a minimum distance of diffractions. Okay, suppose for a distance, now for the two cases எங்கெல்லாம் வந்து ray optics valid, எங்க wave optics valid நம்ம பார்க்க போறோம். So for distances much smaller than Fresnel distance, the spreading due to diffraction எப்படி இருக்குன்னா லெஸ்ஸாக தான் இருக்கும். இட்ஸ் வெரி லெஸ். diffraction is smaller compared to beam size. beam size விட எப்படி இருக்கும்? ஸ்மாலராக தான் இருக்கும் compared to beam size. This is இது ஒரு கேஸ்க்கு. So that only we can say that as when a distance between, so இதை எப்படி சொல்லலாம்னா when distance between லென்ஸுக்கும் ஸ்க்ரீனுக்கும் lens and screen, the distance between lens and screen, இப்போ இதில் இருக்க கண்டிஷன்ஸ் பாருங்க. the distance is much smaller than the minimum distance of diffraction, that is ZF. இப்போ இங்கே என்ன applicableனா ray is valid. Okay, so எப்போ ரேவாக இருக்கும்னா if the light passes through a large aperture, this happens, this is another ray. When a light passes through a large aperture, எதுக்காக நமக்கு லார்ஜ் அபர்ச்சர் இருக்கோ ஆல்ரெடி படிச்சாச்சு. லார்ஜ் அபர்ச்சர் லைக் a lens, mirror or prism. Lens, mirror and prism. ஓகே, அதுக்கு எல்லாமே என்ன கேஸு நம்ம ரே தான் யூஸ் பண்ணியிருக்கோம், ரே ஆப்டிக்ஸ் நம்ம வச்சு பார்த்துருக்கோம். அப்போது மிரர்லேயும் சரி, லென்ஸ்லேயும் சரி, ப்ரிசம்லேயும் சரி நமக்கு எல்லாமே ரே கேஸ் தான் வேலிடாக இருக்குது. பட் வேவ் கேஸ் எங்கே வேலிடாக இருக்கும்? ஸோ இப்போ இது ஒன்று முடிஞ்சுது. ஸோ திஸ் ஃபுல்லி ஃபார் த கேஸ் in which we will use the ray concept, but wave concept எங்கே யூஸ் பண்ணுவோம்? இதை அப்படியே உல்ட்டா பண்ணிக்கங்க. So the distance is much larger or greater than the minimum distance of the diffractions, then the spreading due to the diffraction is larger. So அப்போ நமக்கு என்ன கேஸ் ஆகும்? அதை அப்படியே சேஞ்ச் பண்ணுங்க. So for distances much larger than ZF, the spreading due to diffraction is larger. The spreading due to diffraction is greater or larger. Okay, so that is, we can say the distance is much greater than ZF, larger than ZF. Then இங்கே ரே வேலிட் ஆச்சா? இப்போ இங்கே என்ன வேலிட் ஆகணும்? வேவ் கான்செப்ட் இஸ் வேலிட். அப்போ எந்த சிச்சுவேஷனில் நம்ம வேவ் சொல்லணும்னா, ஸோ வேவ் எப்போனா when a light is passes through passes through hole or slit, that is like a aperture. So that only we are saying as aperture. அந்த ஹோல் இல்லை ஸ்லிட் என்ன சொல்லுவோம், அப்பர்ச்சர். அப்போ நமக்கு ஃபைனல் ஃபார்முலா கிடைச்சிருக்கு. வாட் இஸ் த ஃபார்முலா? ஸோ Z is approximately equal to a square by lambda. நம்ம ஃபைனலாக அதான் ப்ரூவ் பண்ணியிருக்கோம். ஸோ this shows that ray is valid in the limit of wavelength that tending to 0. Okay, so இந்த லாஸ்ட் கான்செப்ட் தான் நமக்கு இந்த ரெண்டு லெசனையும் சேர்த்து கன்க்ளூஷனாக கொடுக்குது. த வேலிடிட்டி ஆஃப் ரே ஆப்டிக்ஸ், மேக்ஸிமம் ரே ஆப்டிக்ஸாக நமக்கு எடுத்துப்போம். ஸோ இந்த வேலிடிட்டி ஆஃப் ரே ஆப்டிக்ஸ் சொல்கிறதுக்காக இப்போ என்ன பண்ணியிருக்கோம்னா, நம்ம ஒரு ஸ்லிட் எடுத்திருக்கோம். தட் இஸ் அப்பர்ச்சர் விச் இஸ் நதிங் பட் அ ஸ்மால் ஹோல். ஓகே, ஸோ திஸ் அப்பர்ச்சர் ஆஃப் திக்னஸ் ஆஃப் வித் A which was illuminated by monochromatic source having the parallel beam wavelength. அப்போ அந்த monochromatic sourceலேருந்து வர parallel beam wavelength அந்த ஸ்லிட்டை illuminate பண்ணியிருக்கு. After illuminations, then the diffraction is observed on a screen at a point P, making an angle theta. So the angle theta is nothing but the angle of diffracted beam, that is theta is equal to lambda by A. In a previous class we have seen in a single slit. So the theta is the angular size of the bright central maxima. So in traveling a distance Z, the diffracted beam acquires the width. So in traveling a distance Z, the diffracted beam acquires the width, that is Z lambda by A. So the width A is equal to Z lambda by A. நமக்கு Z தான் வேணும். So Z is equal to A into A square divided by lambda. So this Z is nothing but Fresnel distance, because summing of all by using integral calculus we can find the minimum distance of diffractions. So the Fresnel distance is also called minimum distance of diffractions. So இப்போ நம்ம வேலிடிட்டி பார்க்க போகிறோம். டூ கேசஸ், ஒன் இஸ் ரே, another ஒன் இஸ் வேவ். எப்போ ரேவ் யூஸ் பண்ண போகிறோம்னா, லிசன், ஃபார் டிஸ்டன்சஸ் மச் ஸ்மாலர் தென் த Fresnel distance, for distances much smaller than the Fresnel distance, that is minimum distance of diffractions, then the spreading due to the diffraction is smaller. அதனால diffraction எப்படி இருக்கும், லெஸ்ஸராக தான் இருக்கும், because wave length அந்த minimum distance inversely proportional. Yes, so when the distances is much smaller than the Fresnel distances, then the wave case is valid. So it is nothing but a distance between the lens and screen. Dingiradhu enna lens ku screen ku naduvana irukka distance. So a ray concept is valid. What are the phenomena? So namak lens la paathirukkom, it's a concave lens and convex lens, and the concave mirror and convex mirror, also in a prisms, then the combination of lenses and the optical instruments. So the ellathilum we are used to only the ray concepts, but the wave concepts only in these cases it is inverse. If the distances are much larger than the Fresnel distance, which is spreading out due to the diffraction also larger. Okay, so அப்போ இந்த டிஸ்டன்ஸ் அதிகமாக லென்ஸுக்கும் ஸ்க்ரீனருக்கு டிஸ்டன்ஸ் அதிகமாக நமக்கு என்ன ஆகுது, லென்ஸுக்கும் ஸ்க்ரீனுக்கும் இருக்க டிஸ்டன்ஸ் அதிகமாக நமக்கு டைஃப்ராக்ஷன் கேஸும் அதிகமாகுது. ஓகே, ஸோ ஸோ வேவ்னா எப்போ சொல்லுவோம்னா, when a light is passes through a hole or slit. இப்போ பார்த்தது இது வேவ் கான்செப்ட். ஸோ ஜென்ரலாக நம்ம இது வரைக்கும் பார்த்தது the Fresnel distance is approximately equal to A squared by lambda. So what this formula conveys, this shows that the ray is valid in the limit of the wavelength that tending to 0. அது 0 கொண்டு வர வரைக்கும், then that is to get the central maximum bright. Okay, so next we are going to solve the examples, followed by the examples book exercises. Coming to the book example. Now just now we have seen the validity of ray optics. So related to the concepts only we are going to see this example. So I am not coming from the first example, I am going in the reverse order. Make sure relevant to the topic only I am teaching this example. Okay, so I am coming from the last to the first sum. Look at the seventh example. For what distance the ray optics is a good approximation when the aperture is very less? What is the width of the aperture? 3 millimeter, and the wavelength, incident parallel wavelength from the monochromatic sources 500 nanometer. So first you write the given data. So they given the width. What is the width? It is 3 millimeter. that we can write it as 3 into 10 to the power minus 3 meter. And the incident parallel beam wavelength from the monochromatic source is 500 nanometer, that we can write it as, nano means 10 to the power minus 9 and 100 10 square, so 5 into 10 to the power minus 7 meter. Okay, but what they are asking, for what distance the ray optics is good approximation when the aperture is less width and the wavelength is 500 nanometer. So the incident wavelength comes under the visible region only. It may goes to the yellow region, nearly yellow regions. So we know that, what is it? The Fresnel distance. What is the Fresnel distance? It is nothing but a square by lambda. So a is the width. What is the width? 3 millimeter. So 3 into 10 to the power minus 3 meter, the whole square, divided by the wavelength, it is 5 into 10 to the power minus 7 meter. So bring the square inside. It is 3 square into 10 to the power minus 6 meter square, divided by 5 into 10 to the power minus 7 meter. So in this meter and the meter square, meter into meter, 1 meter cancel away. Then 3 3s are 9, 9 by 5 into 10 to the power minus 6. The denominator value bring to numerator, it is a plus 7 meter. So 9 by 5, what is the value? So 9 by 5, 1 times it is 5, remaining 4, 40, so it is 8 times. So 1.8 into 10 to the power 1 meter, or 10 to the power 1 is nothing but 10. So 1.8 into 10 is nothing but 18 meter. So we get the Fresnel distance, it is 18 meter. So even with the small aperture, the diffraction spreading out can be neglected the diffraction can be neglected for many meters in length. Even நமக்கு எவ்வளோ லென்த்துக்கு எவ்வளோ மீட்டர் லென்த் இருந்தாலும் the diffraction is spreading out even for a small aperture. So the ray case is applicable here. Okay, so here we use the Fresnel distance. So this is for the concept ray. So ray is valid here. Okay, புரிஞ்சுதுங்களா? The next two question அப்படியே ரிவர்ஸ்ல. Question number 6. Assume that the light of wavelength 6000 Armstrong. So yellow க்கு பக்கத்துல இருக்குது. So orange, nearly to orange. So the wavelength is 6000 Armstrong is coming from the star. Actually the light is coming from the star. What is the limit of the resolution of telescope whose objective has the diameter of 100 inch? So நமக்கு தெரியும் telescope, this is a star. From the star the light is coming towards the telescope. So this is the objective lens and this is a eye lens. So from the star this much wavelength of light is entering to the larger aperture of objective lens. Now they are asking you to find what is the limit of the resolution. So the telescopic resolution we have to find. Okay, listen. First we'll write the given data. So what is the diameter of the objective lens? It is 100 inch. So 100 inch telescope, so which is equal to the aperture effective diameter. So 2a, that is equal to 100 inch. Okay, so 2a is equal to 100 inch, but what is the unit of the length? It is meter. So converting the inch into meter, so 2a is equal to 100 into 1 inch, how many centimeter? It is 2.54. So multiplying 2.54 centimeter, we'll get the value, it is 254 centimeter. So from this, the width A is equal to 254 by 2 centimeter, which is equal to 127 centimeter. So we found the width. The next, incident wavelength. What is the light coming from the star? It is 6000 Armstrong. So that Armstrong is converted into meter, so which is nothing but 6 into 10 to the power minus 5 meter. Minus 5, not meter, centimeter. I converted into centimeter. Since here the width is given in centimeter, so this value also instead of meter I am converting into centimeter. So this value is equal to 6 into 10 to the power minus 7 meter. So 10 to the power minus 2 means centi. So 10 to the power 5 into 10 to the power minus 2 goes to 10 to the power minus 7. Okay. So already we know we want the resolving power, no? Yes. So we know already that f into delta theta, yes, f into delta theta is approximately equal to r naught, okay, which is approximately equal to 0.61 into f lambda by a. So f is in both the sides, we can eliminate. So the final formula, delta theta is approximately equal to 0.61 lambda by a. Then substitute all the value. 0.61 into, what is the wavelength? It is 6 into 10 to the power minus 5 centimeter. Then angle, no, it's a theta, that is a radian. So radian is the unit for angle, divided by, what is the a? It is 127 centimeter. So centimeter cancel. Then finally the delta theta is approximately equal to, after the simplifications, then we have the value, it is 2.9 into 10 to the power minus 7 radian. So we found the value. So the resolution limit of this telescope is 2.9 into 10 to the power minus 7 radian. Moving to the next question. Next question, that is from the first example. Okay, once again we are coming from the Doppler effect. Okay, this question is related to the Doppler effect. Look at the question. What speed should a galaxy move with respect to us so that the sodium line at 589.0 nanometer is observed at 589.6 nanometer. So அப்போ இதனோட டிஃப்ரென்ஸ் இதில் கிடைக்கிறதுக்கு பதிலாக இந்த இதில் கிடைச்சிருக்கு, which means the light is coming from the star, it is yellow light. Okay, ஸோ அப்போது கேலக்ஸி எந்த ஸ்பீடில் போயிட்டுருக்கோம், whether it moves towards us or away from the earth, at what speed should a galaxy move with respect to us. அப்போ கேலக்ஸி மூவ் பண்ணுற ஸ்பீட் நம்ம calculate பண்ணணும். ஸோ அந்த ஸ்பீடு டுவார்ட்ஸ் us away from us நம்ம ஃபைனல் கன்க்ளூஷன் கொடுக்கணும். ஓகே, ஸோ ஆல்ரெடி we know the relation between the speed of light and wavelength. We know that speed of light is a product of frequency and wavelength, or the frequency is a ratio to the speed of light to the wavelength. So here the wavelength is inversely frequency is inversely proportional to wavelength. So that we can say that the difference in wavelength divided by the difference in the frequency divided by the frequency, that is change in frequency by the original frequency, which is equal to lambda by delta lambda, or we can say that the change in frequency divided by the original frequency, which is equal to minus delta lambda by lambda. Both also same? Yes. Okay, now they given the value, substitute. What is the change in the wavelength? So instead of this, it is observed in this. So the difference is 589.06 nanometer minus 589.0 nanometer, which is equal to plus 0.6 nanometer. So this is the difference in the wavelength. Okay. Also, using Doppler effect, we know the formula. What is the formula? The change in frequency from the original frequency, which is equal to minus change in the wavelength from the original wavelength, which is also equal to minus of the radial velocity divided by the speed. Now compare these two equations. Okay, on comparing these two equations, minus and minus, both sides it is common, so we can eliminate. We want the radial velocity. What is the radial velocity? How much speed the galaxy is moving. Therefore the radial velocity is speed of light in change in wavelength from the original wavelength. Then substitute all the value. Speed of the light is 3 into 10 to the power 8 meter per second into change in the wavelength, already we calculated, it is 0.6 nanometer divided by the original wavelength. What is the original wavelength? It is 589 nanometer. So nanometer and nanometer cancel away. After the simplifications, we have the value, it is 3.056 into 10 to the power 5 meter per second. Okay, so this is the value we'll get. After the simplification, this is the value we'll get. Then we want in kilometer, no? So this we can split it into 10 square into 10 cube. 10 square means 100. Multiply the 100 with this, and the 10 cube is nothing but kilo. So kilometer per second. So we'll get the value after the round off figure 306, from the round off digit 306 kilometer per seconds. So this is the speed of galaxy. So the speed of the galaxy is 306 kilometer per second. So which is not moving towards us, away from us. So moving away from us. It is moving away from us. Okay. So this is the formula we got from the Doppler effect. Okay. So using Doppler effect only, we got the radial velocity value. Then next question. Listen. This is from the double slit. Two slits are made 1 millimeter apart. Slit S1 and S2 both also separated at a distance of 1 millimeter, and the screen is placed 1 meter away. Okay. And what is the fringe separations when a blue-green of the light wavelength is used? So the incident light is the blue-green light. It's near to the blue and the green, having the wavelength 500 nanometer. If we use the particular light, okay, on the two slits of the thickness, slit width is 1 millimeter, then the slit is separated from the screen is 1 meter. Then what we want to calculate? What is the fringe separations? So we know already fringe separations for a Young's double slit. So fringe separation, it's nothing but a fringe width. So fringe separation, which is equal to lambda d by d. Lambda d by d. What is the wavelength used? It is 500 nanometer. Nano means 10 to the power minus 9 meter. Into distance between the screen and the slit is 1 meter. Divided by the distance between the slits is 1 millimeter. Milli means 10 to the power minus 3 meter. So this meter and this meter cancel away. Then 500 is nothing but 5 into 10 square into 10 to the power minus 9 meter into 10 to the power plus 3. The minus 3 goes there, plus 3. Then after the simplifications, it is 5 into 10 to the power minus 4 meter, or you give 0.1, that is 1 by 10 to this value. It become 0.5 into 10 to the power minus 3 is nothing but milli, then meter. So this will be the fringe separations. Okay. This is the continuity of the next question. So we know the third questions. In the third questions, two slits, that is in Young's double slit experiment, two slits which are separated 1 millimeter apart from the screen is 1 meter. Then what is the fringe width? We have calculated. And here we know the distance of the two slits. Distance between the two slits, it is 1 millimeter. Listen to these questions. So in the previous questions, what should be the width of the each slit? Okay, we want to find the width, that is A, width of the each slit, that to be obtained the 10 maxima of double slit pattern. This is the important keyword, 10 maxima of double slit pattern within the central maxima of the single slit. So within the central maxima of a single slit, so what is the 10 maxima of the double slit patterns? Okay, so solution. So from the keyword, actually we want A naught is equal to lambda, A theta is equal to lambda, and theta is interference angle theta is equal to lambda by A. Okay, and what they given to obtain 10 maxima of double slit experiments. So that is 10 maxima of double slit experiments. So 10 maxima of double slit experiments. Okay, so in this formula, 10 lambda and 2 lambda. Lambda is common on both the sides, we can eliminate. Then we have 10 by d, which is equal to 2 by a. And further we can simplify with the table. So how much times we'll get? 5 by d is equal to 1 by a, or take reciprocal on both sides. After taking the reciprocal, we have a by 1, which is equal to d by 5. So what is the distance between the slits? Already we have solved. Question itself they given, it is 1 millimeter. Therefore a by 1 is nothing but a. So the width of the single one slit, which is equal to, what is the distance between the slit? It is 1 millimeter. 1 into 10 to the power minus 3 meter divided by 5. So 1 by 5, which is equal to 0.2 into 10 to the power minus 3 meter, that is 0.2 millimeter. Therefore, the width of the single slit in the double slit is 0.2 millimeter. In this case, okay, we did not include the value of the wavelength and also distance between the slit and the screen. So both also we are not included. So that values are need not. We don't want the wavelength of the incident light, and also the slit is separated from the screen with the distance d. That both we didn't use it. Okay. So using the third questions, we want to obtain 10 maxima of double slit experiment within the central maxima. So this is a concept. 10 maxima of double slit experiment with 10 maxima of the double slit pattern, 10 maxima of the double slit pattern within the central maxima of the single slit. Okay. So using this concept, we have eliminated the wavelength on the both side. Then using 5 we are reduced. Then we have taken a reciprocal. After that we have substituted the distance between the slit. Finally we obtained the width of the slit. Next we are moving to the book exercises in next class. Thank you.